All right. Well, thank you everybody for joining today's ELISA Seminar talk on Cregit. And the talk will be given by Professor Daniel German. And Professor Daniel German is a professor of computer science at University of Victoria. And we're very delighted to have him join today's as a speaker to tell us all about the tool he's developed. With that, I'll pass the baton to Professor Daniel German.
Yeah, so welcome. The main reason for this talk is Kate Stewart and I have been talking about the tool and the data that we have been generating for a very long time, and the potential use by ELISA and the projects that it might have. And so Kate felt that it was important to give a small introduction to the tool and what we have been doing for all these years. And so Kate, do you want to add something to it?
Sure. Basically, there's been a lot of discussions as we start looking at the code of the kernel and the traceability and so forth, and people saying, well, they don't know why certain changes were made and how things were made and so forth, because the kernel is huge. And what the things that Cregit does is it started off looking at exactly who created which commits and being very precise, much more so than at the git blame line level, as to what was committed, and then linking back to the commits, and in some cases even linking back to some of the discussions, which for people doing security work gives them a bit more context. And then for people who are trying to do the analysis for safety is also some of the information that people have been looking for. So given this tool is there and available, and that we have been tracking the kernel now for a couple of years, it seemed that it was worthwhile see if we could get some of the other analysis that's going on to be working with this. Okay.
Yeah, great. And let me give you a little bit of context of this. And I'm a professor at a Canadian university. My research for the last 20 years has been primarily the intersection of open source software development, intellectual property, and what we call mining software repositories. So extracting information from archived software development, and then trying to understand, really, that's the important question, trying to understand how open source has been able to be successful through the years. 20 years ago, it was not that obvious that it was going to be. And now we just take it for granted. And so that's a little bit of the context of where I'm coming from. When Git came out, we were some of the first to do research on it. And one of my PhD students was one of the first to look at incremental code reviews, what we typically call now code reviews today, and the difference between those and the ones before the Fogel-style code reviews. And so at that time, we were interviewing developers of the Linux kernel. I'm talking about 2006, 2007. And the Mozilla Foundation to try to understand how the code reviews that they were starting to introduce were more effective than the previous ones. And I'm talking within the context of Git. And so we have been looking at Git for a very, very long time. And I have built a very good relationship with Kate, and so we have worked on different projects. And at some point, the important question that Kate and the Linux Foundation had was, we need to understand better the history of the kernel and how can we improve it. And so that's essentially the context where Cregit was born. And so the purpose of today's talk is just to introduce you in terms of what it is and potentially answer questions that you might have regarding what we have done and the availability of data that we have regarding the Linux kernel. And so we have a repository for Cregit. So Cregit is open source, and it's really a collage of smaller tools. And my job is not to be a software developer. My job is to have ideas and materialize them, and Cregit is the tool to be able to do that. And It has been extremely reliable with respect to the kernel, and some of my colleagues have also used it. And so it's a little bit rough on the edges, but it does what we expected it to do, and I'll show actually some of that. Now, some people also call Cregit the HTML views that we have of the kernel, and that information is extracted via Cregit, and we call this the Linux source code and the Cregit sources, to be more specific. And I'll talk a little bit about the relationship between both, because most of the people will be interested on these HTML views that we have and of the kernel rather than of the tool to be able to do the extraction. And but by describing the tool, you will be able to better understand what exactly we are doing. Okay. And Git is now the de facto standard to do version control. There's still some people that use other tools, but effectively, open source has really embraced Git as the main tool. And one of the things that is really powerful about Git is that it's agnostic to the files that you put. And as long as they're text-based, it's an extremely, extremely valuable archival tool. You can essentially archive any kind of textual information, and you will be able to get historical information and deltas, blame information, etc. With it. And that's one of the reasons that Git has become even popular in areas way beyond software development. It's very popular now with people doing Markdown and having notes in Markdown and storing their notes via Git. So be able to actually do rollbacks or verify when something has been added, etc. And but one of the benefits for some of us who are trying to understand how changes happen is essentially the ability to do diffs and perhaps more importantly the ability to do blame. And so blame has been a very, very valuable tool to researchers who are trying to understand how software development is done, and also to the developers of the software. Although I think that the developers already have an intrinsic knowledge of who does what, so it's just actually a tool that is less important for them than for us, the researchers. And but one of the major disadvantages of version control tools, Git included, is the fact that it does blame at the line level. And it's agnostic in terms of the type of files that it maintains. So the problem is that every time that you get information out of it is by line. And so that has the potential to occlude information. So if you modify a line and you only modify few characters on that line, then the whole line now is attached to that particular commit. So that was one of the challenges that we face, because in reality, what we really want to know is who is responsible for adding each one of the tokens that we have in a particular line of code, and how we can actually retrieve that information and assign those tokens to the actual author, well, commit, and therefore, by consequence, the author of that change. And they also give us a much more fine-grained history of the software development than just looking at the lines. A typical concern for many years has been that you can just do reformatting of the code, and then you lose the actual owners of that code. And Git tries to protect from that, so you can actually do git -w blame, and that will ignore white space. But you could still break a line into two lines and or join two lines into one, and then it will be impossible to do that with the default tools. You'll have to do some extra manipulation of the output to be able to determine our original creators. So there are lots of potential issues with respect to the fact that you basically track lines. You don't track tokens in Git. So what we really wanted to do was the following. So let's assume that you have a function. So what we wanted to do was to actually break this function into a sequence of tokens. And this is the way that we have been doing that transformation. So for every token, we have a generic type of the token. So I think that's a little bit outdated, but it still works. So for example, this is an argument list. So that's actually the beginning of the parentheses. So it tells you we have an argument list that comes next. And then the token that we are on their interest is a parenthesis. And then we have a name, an argument, an expression, et cetera, et cetera, et cetera. So we use a relatively lightweight tokenizer, and that is able to recover from error. That's also important because if the code is not compilable, we'll still want to be able to actually do the tokenization and not fail, because we need to convert every single source code to its corresponding token version. And then from this, what we really have is that we can create two different histories, two alternate histories of the same source code. So above, we have the history, the blame according to line, and below I have it by token. And so you can see here the same version that I just showed you, and then the commits that correspond to that. And I'll explain actually how we do this. And so the advantage of this is that now I can actually, I'm able to say, oh, so these two tokens come from this commit. This token comes from this commit, and this token comes from this commit. So I can actually break them down. And what becomes interesting is that now what we see is that this commit was the original one, and it started to be replaced. Some of the code that it added, it started to be replaced by the other commits. And so now we can actually see that these tokens all correspond to this commit, and then all the others are starting to be just improvements over that source code. So let me go quickly, and so if you have any questions, let me know. And so I'm not in the computer that is in Zoom, so I'm not actually looking directly into that. And so just speak. And so let me explain now very briefly about how this is done. And so we have a paper that goes into the details of this, and the tool is now relatively old. So I think that we have 8 years since we started building it. And this paper is already from 2019. And so it's really nothing new. And surprisingly, the tool has been stable, and we have been able to actually process the kernel without any problem for the last 5 years. Okay, so the basic idea is that if we have a file and we create a view of that file, so the view can be anything that you can think of that is text-based. You could just extract the identifiers. We have done that. So for example, you can say, just give me the type signatures of any function that is in this file. And or in the case of the way that we use it currently is like the view is the tokenized version of the original file. Like what we have currently that I was showing you. And then what we do is that for every commit in the original repository, we create an alternate commit in a different repository that corresponds of committing exactly the same files, but instead of the original text of the file, we commit the view of the file. Okay, so remember, the view is a text-based, text format version of the original file. It can be anything you want. So it can just be, give me the comments of the file, or it can be, give me the first 10 lines, or give me the names of the functions that they're declaring this file. So anything can be. So then for every commit in the original repository, we create an alternative commit. And then we can actually reproduce the original repository. So we take original repository and we create a view repository, an alternate repository with that. So the advantage of doing this is that we are not extracting data into a database or bunch of files that then you have to process. What we are doing is creating another repository that then you can query using Git tools to be able to actually understand its history. But now the history that you have is the history of the view rather than the history of the original source code. I believe that this is the major contribution of our work, to basically say, look, Git is extremely powerful, that if we actually can create a view of the repository, we can actually track the view of the files by doing that. And that actually makes it extremely easy to implement and deploy, because we can, our tool outputs a repository. It doesn't output a bunch of files that you have to understand. And then from this repository, you can do the work that you want. I'll explain that a little bit in a bit. So this, for example, is a file that we actually process. So the left-hand side is the original history. The right-hand side is the tokenized version of the history. And so I already showed you this. So this is essentially the difference between doing the per line and per token version of the repository. So of course, if you go to GitHub, you get a little bit of this already, because in GitHub you get the view of the diff, and then you actually get highlighted the token that has been modified in that particular, or the tokens have been modified, added, or removed in that particular commit. And but that's just an addition that GitHub does on top of Git, and of course that's actually not implemented in the tool, because the tool wants to be agnostic in terms of the source code. Now, in our version of the repository, so this is the same commit, and so the one above is the original one, and the one next is the one in our repository. So one of the things that we do is that we actually add a reference to the original commit. And so the original commit is embedded into the metadata, into actually the commit log. So when you actually scan the original, the tokenized version of the repository, you can very quickly go and refer to the original commit. So that's the way that we actually link one repository to the previous repository. So let me actually just be a little bit more specific and tell you a little bit about how this is done. 6.9. So this is our tokenized version of the repository, and it's essentially the same commits, but the moment that you modify the content of a commit, the hash, the ID of the commit has to change. So that's why we needed to add the label. And so this will be the commit ID in the original repository. Let me actually add the -p option to this, so we can actually see some diffs. Let's keep this ones that are a bit large. So you can see, for example, here this commit, and we actually label comments, so that's important. So for us, a comment is just one token, and so we basically just remove lines in between and just linearize comments. And above, you can see that this commit actually added value and so this actual token. And let me just go to and see if we can find something smaller. So one of the challenges with the version with the history in token base is that it's significantly richer. So it's around 7 times richer than the original one. So diff struggles. So diff is actually much slower, and blame is also by consequence much smaller than the original one. And here's actually an identifier gets added. We also added, for the sake of traceability, extra markers. So this, the capitalized tokens on the left-hand side. So the left-hand side is the type of token. Then there's a pipe, and then in the right-hand side there is the actual value. And but if the left-hand side is capitalized, like DECL, like I'm highlighting here, we add those ones, and the reason is that we actually want to know where functions start and where they end, because it makes actually easier for us to scan the source code when we're looking at the tokenized version. Otherwise, then it's very, very difficult to know where functions start and where they end. So these DECL are just essentially our extra addition. So, and that's actually an important part of these views, that the views can have any information that you want as long as it's text-based, because we need to be able to actually use the to control them. And so here, for example, you see this is a removal of a sequence of tokens. So that's essentially the way that it works. Now, from that, what we do is we create this view. So let me actually go from the beginning and
We have one question coming in, Daniel.
Yeah, go ahead.
Minor question, since we do not use, so it's minor question, this is coming from Martin Hale. Since we do not use Git for older projects, but Subversion has the blame feature. Would it also be possible, probably using this feature, to do the same analysis on a Subversion repository?
This question has two layers of an answer. The first one is that what we're doing here, there's nothing intrinsically unique to Git. You could reproduce another repository. So if given the history of a repository in any version control, you can create another repository with the same information, with the same commits graph. The easy solution for, so now that's with respect to the ideas, specifically with respect to Subversion and other version controls systems, is like you can actually take that history, convert it into Git, and then do the conversion using Git. Sorry, using Cregit. And so you have that history. But now you're actually moving into the realm of Git. And that's the separation kind of the ideas versus the implementation. So Cregit only works with Git. It's actually why it's called Cregit. If you ever search for Cregit, and just make sure that you tell Google that you're spelling it correctly, because it will actually want to search for credit instead. Okay, so any other question?
No, he says thank you.
And so this is our HTML views of the Linux kernel. And so we call this the Cregit source code. And so the idea here is that Cregit has not, sorry, let me start again. So most of the developers, especially the core developers of the kernel, are extremely good at using Git. Git is fundamental to their workflow and the success of the kernel. Most of them, they don't need Cregit. And so very few developers, especially the newcomers, are the ones who might be curious in terms of, oh, who is the one working in this area, this line of code, who really modified each one of those tokens? For most of the developers, the history by line is sufficient. And so this information is really created for other people. And that was the original motivation of this. And we wanted to know for specific parts of the kernel who were the true, let me call them true authors, the true committers. Let me call them true committers of the code. Who were the authors of those commits and who were the committers of that code at the token level instead of the line level. And the main reason was to try to understand whether the history by line was contradictory with the history by token. And so that was useful. But now that we were able to answer those questions, it's like, how can we use this information? And this is where these views started to be useful. So the basic idea here is that, what happened? My computer froze. Oh, sorry. I was in a model way. Okay. So what we have here, so this, for example, is a view of the directories. So these are the main directories of the kernel. And fundamentally, what we have is views by authors. So we were interested in authors. So in this case, each one of these directories contains the number of lines, number of tokens, number of files, number of authors who have contributed to it. Sorry, not contributed, number of authors to which we can attach at least one token, because there might be authors whose code has been completely replaced and we don't track them anymore. This is essentially the view of the kernel in its last release, 6.9. We have now 6.10 that we haven't actually processed, but that's coming soon. So these colors are essentially representative of different authors. And unfortunately, the problem is that when you have a lot of files, and it's very, very difficult to, when you have a lot of developers, it's very difficult to have sufficient colors to be able to inspect that. So for example, let's say Alviro, and so we can see here Alviro has contributions in this part. And then if you expand it, you can actually see the top contributors for each one of those. And so think of it as a nice blame view at the directory level. And but once we go into that, and we can go into specific files, and so this one of the richest files in terms of history, dating from the original kernel. And one of the things that we have been able to do is we have attached the history of Get with the history of BitKeeper with the TAR releases of the original kernel. So when we say Linux pre-Git, we actually mean pre-BitKeeper. So it's actually just those TAR files. We wrap them into one commit, and we don't have granularity in terms of who's responsible for that. And but we at least know that they were created at that moment. And so you can actually see the number of developers that have touched this file, and it's one of those that has the largest number. And some of those with very, very few tokens and commits to each one of them. So for example, the very bottom, we have people who have committed once to this file with 1 token contribution. And then if we look at the source code, and the source code is colored according to the author. And so you can see here, and of course, because we have token level information, we can actually see each one of those by different by the color. So for example, if I click on this, I can actually get to see the actual commit, the commit ID, who was responsible for that commit, and then some extra information. And let me try to find one that has a little bit more historical information. And hopefully. So here, for example, so if I click on this commit, and I get the commit ID, and I also get information from LKLM. And so one of the things that we did for a while, another one of our research projects was to try to extract information from mailing list of the kernel such that we were able to link commit IDs in the Git repository to their discussion in the mailing list. And we were able to do it for a few mail lists. The majority of them are LKLM. So if I click on any of this, on any of these links, and let me do that, then it sends me to the particular commit and the discussion in the LKLM of this commit. And the other thing is that if I click on the commit, then I can actually go to GitHub and then see the actual commit. And let me go to so here, for example, so let's say that I want to see this. I can actually go to GitHub, and then I get the corresponding history of this. So somewhere here, we should actually see kernel.c. Promise that some of these commits are a little bit big. So fork.c, so you can actually see it here. So this is actually a commit, and we can actually see the tokens that were modified. So there's 2 macros that were updated, and then 2 tokens, one line of code plus a token replacement. Okay, and so we can also look specifically at authors. So promise, let's try to find Linus here, the pre-Git. So you can see all the code that is still comes from the pre-version control days. And it becomes interesting questions, right? Like this asterisk. So we're able to actually track parentheses, semicolon. So this semicolon, for example, so this actually tells you that this original line comes from that, and the line might actually be modified by many other people. But sometimes even tracking the semicolon might actually be interesting information. We can also narrow by date, so we can actually see all the commits, or we can actually specific authors, and we can actually see what parts were created at which point. One of the things that one person here in Victoria is working on is to add the ability to select by release, because I think releases are more meaningful to most of the people rather than date. In fact, an interesting aspect is that in the last release of the kernel, and we might have commits that they take 1 or 2 years to actually come to the final repository, because that's the time they take to percolate from the original source all the way to the final main repository. So one extra thing I wanted to mention is we also have we have been using it also for more research. So this is a paper that is coming out relatively soon. And so one of the things we discover is that a little bit less than 10% of the kernel commits add or remove at most 5 tokens. And so that tells you the level of maintenance that the kernel has. And so that's the kind of that analysis that we can do. We can go much deeper and understanding exactly what gets changed in a commit. One of the things that we observe is that the types of changes are typically names that change from one to another. You change a call from one name to a different function. Or sometimes you add a parameter, you remove a parameter, or you change an expression. So you maybe add a number, or change a number for a constant, or change a number for another number. So relatively minor changes, but impactful, because most of them, if not all, are bug defects that they are being dealt with. There are some changes that are structural. So, for example, you can add 2 braces and in one of these micro commits, and those braces might completely alter the execution path of the original kernel. So there's very, very interesting aspects with respect to this. And I think that's basically what I have. And let me just finish with this, so you can actually have those are the links, and you can email me, and if you have further questions. And but as I said before, so Cregit lives in GitHub, and then the Linux sources, that's what I was showing you, where you can actually browse the history of the kernel. One of the things that we have with respect to ELISA, one of the things I've been discussing with Kate is the ability to, if you're interested in the kernel, the commit becomes a focal point of development. And so if you have more information about a commit, we have the infrastructure where we can add links to other types of information. So let's say that you have a website that describes how a commit gets implemented. And all we need is just the description that we want to put on the view, and the URL, and then we can add it. And so it's relatively flexible in that regard. And also Cregit allows to link to a particular line of code. And so if you want to actually have a discussion that say, oh, look at this line in this file, you can link to that directly in Cregit sources. Okay. And but that's basically it.
And I'll just add in that the other side of it is linking into things like requirements. Once requirements are there, is something you can possibly start to look at too from the coverage perspective.
Yeah, and that's what I mean about having links. So Cregit doesn't care about anything but commits.
Yeah.
And Cregit sources. So we have the commit, and if you have information about the commit, we can link to that. And it doesn't matter what type of information it is. All we need is a commit ID, a URL, and a description.
Right. And we've gotten a question coming in from Matthew. Has there been any research to map vulnerability fixes that have CVE entries with commits tokens / fixing a bug, i.e. understanding how many bugs and vulnerabilities aren't being tracked by the CVE reporting?
Probably not at token level, but by line level, I know that there are people that they're actually doing this kind of work. Julie Lawal, she has been very active in the kernel, and she's a very well-known researcher on automatic defect fixing. And so she has a lot of work actually dealing with repair on the kernel. 。
Julia's going to be at Plumbers as well this year. So if people are going to be at Plumbers, there's chances to interact and talk further.
Yeah, and I was actually just looking at she had a paper very recently, just continuing the work on repair on the kernel, and she has not done it at the token level, mostly because not a lot of people have been using Cregit and in the research. And one of the interesting aspects that I look at when I started doing this work is that the history by token and the history by line doesn't really change much who are the most important developers. And the important developers commit lines and commit tokens, and they're still important. What it changes really is the people in the past starts to get erased by the people in the present when you go by line, especially because all of these lots of modifications. But the reality is that most lines in the kernel are never modified. It's like you open a brace, the brace will never be modified. And that's actually a very interesting question. So I never really look into that. Of a given file, what is the probability that, so of a given line, what is the probability that it will be modified?
Mm-hmm. There's certain parts that are definitely very stable, static.
Yeah, the drivers are very stable. The drivers, they get in and nobody else touches them but the author.
That could well be.
That file that I was showing you, fork.c, that is an outlier. And we have files that maybe have 2 or 3 authors, and one of those authors is the licensing information.
Mm-hmm. Which has been there for a long, long time.
Yep.
Okay, does anyone else have any questions? Feel free to unmute and just ask questions directly if you've got them. Okay. And I guess the only last little comment is sort of the directions, future directions, Daniel, for this tool. I think we've been talking about some.
For the tool does what it's supposed to do, and it does it well. And so the tool doesn't need modifications, at least that we feel. It takes a repository, creates another repository. The area where there's a lot of room for improvements is the HTML views.
Mm-hmm.
And because that's the information that most of the people are interested in. They're not interested in converting the Linux repository to another repository. We can do that. The nice thing about it is that once a version is released, that release will never change. So it only has to be done once. But it's extremely rich history. So there are many, many different ways to present this information, dice it, and we're just exploring the surface. And this was basically a proof of concept that we can have this information and deploy it. One of the challenges these days for the kernel is that we need to do the parsing for Rust, because Rust is going to become a major language in the kernel. And so it will actually increase, the use of Rust will increase with time. And hopefully by 6.10, and we will have Rust processing. And because what we need when we do the transformation from repositories, we need a parser. Sorry, let me rephrase that, a tokenizer, because it's not really a true parser. We are only interested in tokenize and at the type level. And so that's a much simpler task. We have been successful at using it with Python. Go, Kubernetes used it at some point. I don't know if they still use it. And so we actually had a Go parser for it. And but most languages today, they have mechanisms to do the parsing. And so it's not difficult to do that. But I don't consider that to be part of Cregit. Cregit basically says, just give me the filter. Whatever you want, I'll do it. And so, for example, one of the things I did many years back, and I have a GitHub repository with that, is just tracking identifiers, just tracking functions, only functions, just the name of the function. And what becomes interesting is that I actually know who is the responsible for running a function and who are the people who are modifying the signature of that function. And the Cregit repository, all it has is just the function names and no source code. One of my colleagues is developing kind of what I see as the next generation of these tools, and what he's doing is being able to separate source code into into different files. So he says, well, a class is sufficiently important that it should actually live in its own file, but maybe I can actually extract from a class each one of the methods in a file. So he has one file for the main attributes of the class and one file for each one of the methods. So he can actually track historically with blame just one function at a time. And then that actually becomes very useful, especially in Java, where the file location changes all the time, depending on the name of the class. So now you actually track just the function, and even if it moves from one file to another. And so it's much easier to detect clones. It's much easier to detect code movements than with traditional Git history.
Okay, we've got one more question in from Matthew, which is, do you tokenize config kconfig files, or which files types are
No,
not?
we haven't had the interest to do that.
Okay.
Yeah, it's like we were not interested in that information. We were interested only in the C files and the H files.
Which other files are not tokenized? Like if I was going to do a straight version to version change analysis, is it just C files?
It's just C files. At this point, it's .c and .h.
Okay, so you'd
And,
welcome contributions of tokenizers for those other ones?
Sorry, can you repeat the question?
But you would welcome contribution of tokenizers for the other files?
Yes, and because now that we're going into Rust, we need to actually be able to implement a dispatcher of the type, because it's simpler if you only have one tokenizer, because you basically say, if you give me C files, and then I will. So if you wanted to tokenize with only one type, all I have to do is dispatch this tokenizer. And if we have different file types, then we need to, in the tokenization part, what we have is a dispatcher that basically says, what type is this file? And then just run the corresponding tokenizer.
Okay, thanks.
And but yeah, but that's actually, that's the process that we do every 3 months. So every 3 months, we essentially run Cregit on the kernel, create the new repository, and from that we create the HTML views.
Excellent. Okay. Well, I think we're starting to lose people at this point now. But if there's no more questions, we will definitely say thank you very much. Go ahead, Ben. Thank you, Daniel, for going through
You're welcome.
this.
Yeah, thank you, Daniel, and thank you everybody for joining today's seminar. And we have other ELISA webinars coming up. Just look on our website at events under elisa.tech, and you'll find other upcoming events with us. Thank you so much.
Thank you.
Bye.